So we will start with a discussion of x86's memory addressing mode. And the addressing mode of x86 is not very straightforward. After all, it's a CISC instruction set. So the standard format is that there is a base register. In addition, it also takes an index register. For example, the base register could be the starting address of an array. The index register could be the index of the array, like AI. So A is the base and I is the index. And then the scale is that it could be an array of integers or an array of doubles or an array of characters. So in the case of a char, it is 1 byte, so the scale will be 1, right? So on and so forth. 1, 2, 4, 8. And finally, on top of this, we can add scalar displacement. So the net address that is computed is base plus index times scale plus displacement. So not all of these fields are compulsory. In fact, it is possible to just specify the displacement. In that case, it will become like an absolute address. So that is possible. So as I said, not everything has to be specified. So let us look at a few examples. So this is in the AT&T format. So the first one actually uses all. So it has a displacement, it has a base over here, and then an index and a scale. So it has all 4. Alright. Essentially, the displacement you are adding to the base. So you can start from some other base if you wish. So it allows you a lot of flexibility. In this case, you only have the base and the index. Then in this case, you only have the displacement and the base. So you have only, in this case, the displacement and the base. So the moment you have so many types, it becomes reasonably easy for the compiler to generate really efficient code. Because as you can see, there is no necessity for actually reading the index, multiplying it with some number, right, which is the size of the data type, adding it to the base. So all of this is doable in one instruction itself. So the same operand kind of specifies all of these fields: displacement, base, index, scale, and the address is computed, and this happens internally. So as you can see, a lot is happening in the span of one instruction. So let us now look at a small example of an assembly code for computing a factorial function. So in this case, what we are doing is that we are moving 1 to EDX and we are moving 1 to EAX. So both of them are initialized to 1. Then what we are doing is that we are doing that classic product is equal to product into number. So EDX is equal to EDX times EAX. So the EAX is basically the variable over here, right? The one that gets incremented. It is that one. Product is equal to product times I. So then what we do? Then we increment EAX. This is as simple. So as I said, the source and the destination are the same, right? So one source and the destination are the same. So in this case, it should be EAX is equal to EAX plus 1 gets incremented. Then we compare EAX with 11 because we are computing 10 factorial. If the comparison is not equal, then of course you loop back, otherwise you come down. As simple as that. So the only tricky thing is, kindly bear in mind that the destination is towards the right, is the rightmost operand, because in general we are used to left, right? It's like you're in a country that has left side driving and then you go to a country like the US which has right side driving. So once you can sort of get over this little bit of discomfort, the rest should be fine. So now we'll take a little bit of a detour and look at what is so this was like one appendix of the book, and there's a second appendix, appendix B, and look at the process of compilation and linking and see how it actually happens, and then I will also show you an example. So any large project comprises hundreds of C, C++ files because you have lot of developers, correct? And every developer will write their own files, and then they will write functions to export it to the code that other developers are using. For example, I am writing the code of Factorial, you are using the code of Factorial. So I am the producer, you are the consumer. Finally, what will happen is one large program will be made at the end, which is called the executable or the binary. Both are interchangeably used. So we'll also use both. So finally, to create the executable, which is a.out on Linux, right? It's named that way for historical reasons. So what is it that you are actually doing? What you are actually doing is you have a bunch of these .c files, right? So you can always do gcc star.c, but that is going to be very inefficient, as we shall see shortly. The reason is that you may have just try to compile the Linux kernel, it will take an hour. Every time you don't want to spend 1 hour because you may have changed one file. So you want it to sort of happen incrementally. So what you do is that from a .c file, you actually create a .o file. A .o file is basically the compiled representation of the C file, which is a source code file. So internally, GCC has multiple passes where GCC is the compiler on Linux. It's called again GNU or GNU compiler collection. And as I said, GNU is a recursive thing, right? GNU is not Unix. So the -c option allows you to kind of see a subpass of it. So x.c becomes x.o, y.c becomes y.o, so on and so forth. So you start creating all of these object files. These object files are what? They are essentially the machine code representation of the function. But kindly bear in mind that not all functions will be defined in an object file. For instance, the factorial function may be defined in y.o and x.o may be referencing, maybe invoking the factorial function defined elsewhere. So it is finally the job of the linker to take all the object files and construct one large executable, correct? And in the large executable, of course, as we have seen, there is a memory map with sections. So all the code is put in one section called the text section. So its job is to take all the code and concatenate it. And then at this point, the address of the factorial function will not be known because it is defined somewhere else. But the job is then to fill in those missing addresses. Because now when I've concatenated everything, all the functions are there with me. So wherever they are used, I can kind of do a fill in the blanks over there. So I will have a fully featured self-sustaining binary called, I can give it any name, but let us call it a.out. If I'm not giving a name, that is the default on any Linux system.
So where is the assembly file? Like,
yeah, the assembly file is again like kind of here in the middle. So you can see the assembly file by giving the -S option. But in this case, when you do -c, so what happens? The compilation proceeds in passes. So the moment you have a .c file, you actually create a parse tree. So the parse tree basically parses the C file, checks the syntax, semantics, not the semantics that much, the syntax, the grammar. Then you create an abstract syntax tree which represents the entire program in a tree-like fashion, and then you start doing multiple passes on it to kind of make the representation closer and closer and closer to machine code, and also you apply different optimizations in each pass. So many modern compilers do not actually convert it to assembly per se, but they convert it to some intermediate representation which is very close to assembly, and you can actually see the assembly. And in many cases, many modern compilers actually convert it to assembly, and then the assembly is converted to the object file using a program known as the assembler. So all of this is kind of folded into GCC. So finally, after a set of intermediate representations, you have the .o file. And somewhere here, you can look at the assembly that has been generated. Correct? So the assembly is generated, then the assembler converts it to machine code that is further optimized. Finally, a auto is what you get.
Does the order of the files they have made into the file abstract?
Well, so whenever you are compiling, the question is does the order of specifying these matter? Well, we will see yes and no, but in general, whenever you are compiling, you are only compiling a single .c file. The compilation is always on a single file, and .c to .o is only a single file. It is possible that it will find many functions which are not defined. That is why it needs the signature of the function. That is precisely why header files are important, because it says the definition is not there, I'm fine with it, but at least show me the signature, which will allow me to generate the code. So the signature is like the contract. And once the .o files are there, then when you are linking and making one large executable, then of course you need the definition of everything, even though we'll slightly relax this specific statement later. But let's say for the time being, let's live with the assumption that the .o files are joined and everything is available and visible, right? So what does a .o file contain? So you can run the object dump command, obj dump, and look at what a .o file contains. So you will see that it contains actually multiple sections. It is split into multiple sections. The .text section contains the machine instructions or the C code. Machine instructions corresponding to the C code. Then you have your initialized data, which are your constants and global variables and static variables, ones that are initialized. You could have uninitialized global variables as well. That is your .bss section. Then you could have constants which are kind of not in variables, but things like pi and other things, right, that you have defined. So if there are, or let's say you are printing and then there is a string, right? The string says the value of this is this much. So this string is a constant. That constant has to be stored somewhere. So it is stored in this read-only data section along with comments. There are two important tables within a .o file which are of a lot of importance. So we will look at all of these things when we do a demo. But let's first look at this theoretically, then I will show you the code. The first is the symbol table, which you can easily see. You can either do nm on it and look at it, or you can do an obj dump minus symbs, right? So then what will happen is that you can see the list of all the symbols that are defined in this as well as used in this, but undefined means defined somewhere else. So the symbol table basically contains all the symbols, namely function names and global variables. Some are defined within this .c file, some are referenced but not defined, and those come with a U entry, U for undefined. Then we have a relocation table, which is essentially a subset of that symbol table, the undefined subset, which essentially says that I invoked the factorial function, but there is no factorial function in this .c file. It's true that I have the signature, but I don't have the function itself. It is a message to the linker that while linking, kindly take a look at my relocation table, and you will find that I am referencing the factorial function, but I don't have its definition. So it is the linker's job to find where is factorial and find the address of that. Wherever I am referencing factorial, put the address there. Correct? So that is the job of so this thing is something that, so the linker will essentially read the symbol tables of the rest of the .o files, figure out where is factorial, and then when you concatenate, the factorial function will have an address, and that address comes here. So the question is that how are developers supposed to collaborate in the case that proc.c is using the factorial function and factorial c.c is defining the factorial function. So as we have said, compilers will take a look at every C file individually. Proc.c, which is the user, needs to only have the signature, and the signature in this case is int factorial int. You don't need variable names because you just need the signature. Why is the signature important? Well, the signature is important because maybe you are passing a float to the factorial function. C does automatic typecasting. So float, it will convert to integer. But how will it know that? How will it convert to integer? There has to be some code to do it, right? You have to kind of stick some code into the C compiled version of the program to do a conversion. But then it should know what is the signature of the function, what is it expecting. Only then, whatever arguments you are giving, it can arrange it in that way, convert the types, and invoke the function correctly. The same holds for the return value. So maybe the return value, it is returning a float, but you are putting it in an integer. Again, a type conversion has to be done. So that is why the signature is needed for compilation, right? So what we will do is that we will look at a bad way and a good way. So a bad way is normally what we do in first year class assignments. So which is that, let us say this is a single .c file. I defined a function here, but I'm using it here. Your compiler will give an error saying that at this point I don't know the signature of this function. So what I will do is at the very top of the file, I will define the signature myself manually. I will simply say int factorial int. If it is there in some other file, I can write extern int factorial int. Extern means it is externally defined in some other file. So the main idea here is that the moment I start hard coding things, I can't change the signature. I don't know who's living with what signature. And this is a very ad hoc, impromptu kind of solution, which we do not like. And furthermore, everybody will have to have all the signatures, a lot of replication. The moment there is replication, if you, let's say, let's say you give the factorial function one more argument, you'll have to go and change it in so many places. That is why you have a single .h file which has a bunch of signatures related for functions as well as global variables. Then what happens is that when the moment you do a hash include of factorial.h, the preprocessor which runs it's like a pre-compiler which runs before the compilation, simply does a copy paste. Right, so you can we will look at this. You can do GCC minus capital E. So what will happen is that the entire code of the .h file will kind of get copy pasted into your .c file, and your signatures will be available to you. And .h files are good because you can nicely export your signatures everywhere. So given that we have some idea of the preprocessor now, so it can do other things like hash define would kind of define a sort of a preprocessor variable. A macro is like a preprocessor function that the kernel uses a lot to do actually reasonably complex things. So you can watch an interview of Linux developers where they said that we have modified C so much, it doesn't appear to be C anymore, right? That is mainly because if you see the kernel code, there are so many macros and so many of these shortcuts, right? Like an entire linked list traversal is a single macro. So they have made life very easy for themselves, and we'll see it's very elegant. So where do we stand now? Where we stand now is we have a factorial.c which has a symbol table, and the symbol table in no uncertain terms says that I am exporting the factorial function. I have my proc.c which hash includes the factorial.h file which provides it the signature. And the proc.o will have a relocation table which will say that the factorial entry is undefined or unresolved, which means I'm using it but I don't know where it is. At link time, as we have discussed, the entire code will be laid out. All unresolved symbols will be resolved. So that is the correct terminology. That all undefined is not a good term to use. You should say unresolved symbols, which in this case can be global variables or functions, will be resolved. That's the right terminology. Now there are two kinds of linking: static linking and dynamic linking. All right. So what static linking does is that it basically takes all .o files, including, so we have not discussed the standard library, but let us do that now. So let's say printf. So printf is a function, right, that we are using to render a service. The service is printing to the terminal. That we have not written. That someone has written. And we are only accessing its signature by stdio.h. That is giving us the signature of printf. But the question is that when you create an executable, the code of printf also has to come in, which basically means that a large part of, well, not a large part, but whatever part of the C standard library you are using, a library is basically a collection of compiled functions. So what you do is you take a bunch of .o files and create a library, where a library will have a bunch of functions and variables all defined within it. Okay, so far so good. And so a library is cannot execute on its own, but it's a library of compiled functions. So the C standard library has to be linked along with the rest of my .o files to create one jumbo executable, and then it will run. So we will run these commands and we will see what it does, but basically then it is going to run. So insofar as this executable is concerned, this means that whichever function you call in the standard library or whichever function is mentioned, the code of all of that has to come. So maybe there are like 100 mentions of 100 different functions. All their code has to come into your binary. But in practice, you may be calling only 3. In that case, you will not find such a large jumbo binary to be very useful. That is one reason. And the other reason is that often the code of printf, the object code, machine code, is shared across multiple running processes, right? All of them would be using printf. So what is the need for replication? We can kind of share it. So when we look at virtual memory, we will see that you keep the code in one place and you share it. That is why static linking is not a great idea. But before we proceed forward, let us actually run these commands and let us see what is it that they actually do. And then we will be in a better position to understand why a.out is so large. And as I just discussed, a.out is so large mainly because every single function that it can possibly call, the code of all of those functions is there in a.out, even though in any practical feasible run, you will be invoking a very small subset of them, right? So you need not have such a large one. So we will build an a.out, which is static. We will look at its size and we will see it is close to a megabyte or so. That is why we perhaps need to adopt a different kind of solution. So this is the factorial.h file. So as you can see, what I have done here is that I have said that if the symbol factorial -h is not defined, then you define it, which means that you are stopping it from being included twice. So if it has already been included once, what's the need to include it once more? That's why this is a standard thing, that if this hasn't been defined, you define it, and this is the signature of the function. The factorial.c file basically has a single include. You can include it twice, nothing will happen. And then what you can see here is that you can see the regular factorial function that we all know. So there is no rocket science over here. So proc.c basically includes factorial and calls factorial. That is all. It doesn't do anything more than that. So what we will do now is that we can directly compile them as proc.c and then run it. No problem. What we can also do is that we can create -c proc.c. It will create a proc.o. Then we can create a factorial.c. It will create a factorial.o. Then what I can do is I can compile the, so doing this is tantamount to linking it, and I can run it, no problem. All right. So this is good. So if I, so now let's say I can do a static compilation, which is something like this. So to check whether it is static or not, what I can do is ldt a.out. So it will say it is not a dynamic executable. We'll see in a second what a dynamic executable is. So let us look at the size of this file. It is 768 kilobytes, which it is doing almost nothing, right? It is basically taking the factorial, it is printing it. So it is doing almost nothing. So there is no need for it to actually take so much of space. But if I just do a regular GCC, then its space will not be that much. It will just be 16 kilobytes. That is because it is not what is called a static executable, which basically means that the code of the standard library is not included in the executable, right? It is kept outside. So we will see what that means. But if you do an LDT, you will see that these are the standard library, and this is where the standard library is. It will kind of point you to it. The code is kept outside. So this is known as dynamic linking, which in a second we'll see what it is. But basically the idea here is that a static linking, which is putting all the code, is space-wise, storage-wise, efficiency-wise, a bad idea. So let us now look at, so we will look at the same thing, and but we'll look at it slightly differently. So what we will do is that we will try to create a static library and a dynamic library, and then we'll try to understand the theory behind it. All right. So what we can do is that, let us say I have created a bunch of functions, and then I'll have to give you a bunch of .o files. That is an unwieldy task. It may be a good idea to take all the .o files and create a library out of it. So let me do that. So the AR is archive command, C is for create, 1 is to add it to the library. We'll look at all the options. So I can create a factorial.a out of factorial.o. Factorial.a is nothing but it's an archive. And then what I can do is I can compile proc.o with factorial.a. So then what will happen is that I took the .o file of the program which is using the factorial function, and the factorial function is not in a .o file, but I have put it in a library. A library is a nice thing for encapsulating the code of many .o files. And then I just run it, lo and behold, you will see that the result is the same. So of course we had no doubts, but what I did is I created a static library. So what is there in the library, you can just do an nm and see. You will see that the factorial function is defined in the library. Correct? Now if I start looking at proc.o, you will see that, look, main function is there in proc.o. This is there in its text section. Factorial is undefined, printf is undefined. So it is simply saying that, look, I know about main, I don't know about factorial and printf. Now if you look at factorial.o, it will say I know about factorial. When you link them, let's look at a.out. So of course there are a bunch of things, but it says, look, I know about factorial, I know about main, but I don't know about printf. So we will see. So it doesn't know about printf, but it still runs. That is because of a separate mechanism called dynamic linking, where what happens is you say it's okay if you don't know about printf, but what I will do is that in the place of printf, I will point you to a dummy printf function. The first time you run printf, you actually go to the dummy. The dummy locates printf in some standard library in the system, which is libc.so. something. From there, it will copy the code of printf to your memory space. If it is already there in the memory space of some other process, it will map that to you. This is a very space-saving mechanism, which we will see in a second how that works. So let us do one thing. For creating a dynamic library, the steps are slightly more elaborate. The first is that you want to create a shared library for factorial. So the compilation options are slightly different. What you have to do is you have to give the -c option because you are creating a factorial.o, and -f pick. Pick is position independent code. That is because the code can be placed anywhere. And -o factorial .o. Sorry, so we are doing this. -o is the name of the output. So factorial.o is created. All right. So you can do an nm on factorial.o. It will say that I know factorial. Then what you can do is you can put the shared thing and say that I want to create a shared library. A shared library is a dynamically linked library, as we shall see. It's a DLL. And this is what I want to create out of factorial.o. And factorial.o is compiled correctly, which means that it is compiled in such a way that its code can be placed anywhere in the memory space. So libfactorial.so is now created. Now what I want to do is I want to basically compile everything. So then what I do is I take proc.c and I do this. So what is it I'm doing? I am saying -L that all the libraries will be found in the current directory, or search the current directory first and then search the system directories. Proc.c I want to compile. The library that I want to use is factorial, so I put -l factorial. -L is for the library path, where you search for libraries. -l is the name of the library itself. Correct? So now your a.out is created. Let us see what a.out is. So a.out is saying that there is a libfactorial.so, which I am referencing, but I don't know where it is. But it is there. It is there inside my code. So you have to do a little bit of an additional trick. There is an LD library path environment variable, which says that where the runtime will search for libraries. All right. So in this case, you set it here. Now you do an LDD again. This time it will find libfactorial.so. It will say that it is there in the current directory. And then all that you have to do is just run it. The answer is 6 and its size is small. So what did we get to learn from here? What we got to learn from here is that we can create a dynamic library, where a library is just a collection of compiled functions. And of course, the compilation options are slightly different. It needs to be position independent. Then I need to compile that as a libc shared library. Even when building the a.out, I have to provide two pieces of data. The first is the library path with -L and the name of the library itself with -l. Then my compilation is done. But that still doesn't allow me to run. When I'm running, I'll have to tell the runtime where to search for libraries other than the standard places like /lib and user lib and so on. That is why I set the LD library path environment variable, which tells me that look, search in the standard places, but before that, you search the current directory. It will search that, and you clearly saw the way it works, and now you are able to run. So if I were to sort of look at this, slightly theoretically now, so you may want to look at this specific slide, which shows that the printf function actually is linked to a stub function. Point is that the printf function is linked to a stub function. The stub function is like a dummy printf function, which is called the first time that printf is invoked. The first time it is invoked, it locates the function in a library, which means it searches the library path based on the order of preference, searches the libraries you may have supplied, searches the standard libraries, and then it locates the functions. So it copies the function to the address space of the parent process. But as I said, if it is already mapped, there is no need to kind of waste extra memory space. If it's already mapped and you know the address, then essentially the OS will adjust the mapping such that you also can access it from your virtual memory space. And the stub function locates the library, and then the library locates the function, and then you compute the address accordingly. All right, and then you store the address. So now the address is there in your address space, the function is there, so and the address is stored. So the next time printf is called, you don't have to do this entire exercise, right? All that you have to do is just simply jump to that address because it's anyway mapped. So this is like a shortcut. So we'll look more about this in the virtual memory section. All right, but this is the broad idea of dynamic linking, and you saw how dynamic linking actually happens. So dynamic linking effectively reduced your program size from 768 kilobytes to 16 kilobytes, which is a substantial reduction, right? Massive reduction that you saw. Of course, the process of compiling has a lot of steps. I'm not saying it's a very simple thing to compile, but that is exactly why you have make and cmake, make files and cmake files and so on, where all of these things can be written down, such that in any practical setup, if there are 1000 .o files, you don't have to recompile all of them. You just have to create a few additional .o files and link. Essentially, that's the work, right? That is why you have make files. You automatically figure out which C files have changed based on their modification time. Then you create the .o files, and you may have to create a very few, maybe 1 or 2 or 3, and then you just relink. So a make files greatness is that it automatically figures out what is it that you have changed after the last time you built the entire project based on your file modification times, and then locate the .o files, recreate them, relink, and you're all done. All right, so this is how a large modern C++ project actually works. So we will look more. So we have looked at LDD and obj dump and NM also to look at symbols. So your job is to look at the rest of the three functions, which are readelf, strip, and ranlib. So strip essentially deletes the symbol table. Ranlib, if there are a lot of symbols, it will create an index for it. And readelf, slightly more expressive than obj dump. All right, so you look at these, and we'll look at virtual memory from the next class.